Hello everyone, we are Anurag, Tanuj, and Jialin from Group 14, and today we present a project, Music Genre Classification using Spectrograms and CNNs. Here is our problem statement. With the rise of digital streaming, managing and recommending music have become a more important task. Content providers will want to have effective methods to classify music genres to provide better workflow and user experience. To that end, our project aims to automatically classify music into genres by analyzing audio signals using machine learning architecture. Our dataset comes from the GTZNN collection, with 1,000 audio tracks distributed evenly across 10 genres. Each audio track is 30 seconds long. The dataset also comes with two CSV files, which are a list of 58 features calculated across each audio track, as well as the same feature calculated after dividing each audio track into 10 3-second clips. Here are some diagrams from our exploratory data analysis phase. For example, the violin plot shows the distribution of a single feature across different genres, demonstrating that different genres can have very distinct features distributions that will aid in classification. There are also these waveform diagrams and the male spectrograms. These are generated based on the audio clip. Only these male spectrograms are used in the CNN part of our model. The violin graphs and waveforms are for visualization purposes only. We preprocess the audio by splitting each file into overlapping chunks, 4 seconds each with 2-second overlap, ensuring that our model receives sufficient local information from each sample. For feature extraction, we process both the male spectrograms and the numerical features. The male spectrograms are converted to time-frequency domain, applied with male scaling and reset to be the same dimensions. For numerical features, we extract many of the defining features to be used in the deep neural network part. For data augmentation, we employ time masking and frequency masking to create more varied samples. And as per usual, the dataset is split into 70% training, 15% validation, and 15% test sets with stratification. Here is a high-level overview of our model architecture. It has a CNN branch for male spectrograms, a DNN branch for numerical features, and a combined part that concatenates both to produce predictions. And here is a slightly more detailed description. More on that on the next page. The DNN branch contains 3 dense layers: batch normalization, ReLU activation functions, and dropout regularization with dropout rate of 0.3. The CNN branch contains 4 residual net-style blocks with skip connections. Each block contains 2 convolutional layers with batch normalization, a progressive channel expansion, max pooling, and followed by a self-attention mechanism after convolutional blocks. And there is adaptive pooling for fixed output dimensions. This is a diagram of a single residual block that is used in the CNN branch, with convolutional layers and skip connection. And the graph down below is the diagram of the self-attention mechanism that enhances the feature obtained after passing through the residual blocks in the CNN branch. Continuing on the architecture, features from both branches pass through a final cross-model attention fusion with projections. They are then concatenated and go through a final classification head with fully connected layers, batch normalization, and dropout. The final output uses softmax activation for genre probabilities. And here is a diagram on the final portion described in the previous page. Moving on. We trained the model with 50 epochs with early stopping. Batch size is 32, learn rate is 0.001, and the weight decay of 10 to the power of -5. We use cross-entropy loss and Adam W optimizer with weight decay. In addition, we have a reduced learning rate on plateau scheduler to try to minimize accuracy degradation after plateau. Our model is run on a standard PC NVIDIA GPU with CUDA, and it takes around 3 to 4 hours to train. The final result is the following: 97.96% training accuracy and over 95% on both validation and test sets, a significant improvement over our baseline model. Here is the confusion matrix that demonstrates the model performing well across the board, and the statistics to the right that shows the specific performance on each genre. As per usual, we evaluate using overall test accuracy and per class performance. Among these genres, The model performs best on classical hip-hop and reggae, but falls short on rock music. It often confuses rock music with metal for some reason. But overall, we are still very happy with the 95.8% test accuracy. In conclusion, our multimodal hybrid architecture with attention mechanisms and cross-model learning shows a very promising result, achieving more than 95% accuracy across the board. There are limitations to our approaches though. Our model does not perform well with very short audio clips, and it has confusions over some related genres, which could lead to potential bias. Our model still has room for improvement, such as incorporating temporal models with RNN or LSTM, exploring transfer learning from larger datasets, or extending to hierarchical general classifications, and more. And here's our reference. As before, this is the reference to the GTZAN dataset that is available on Kaggle. Thank you for your attention. I'm happy to answer any questions.